Hi Deepak, can you hear me and can you see my screen?
Yes, sir. Good evening, sir.
Good evening. Okay, we'll start. So this is the 11th session, and the next one was scheduled on next Monday. Uh, that one I have preponed. So the next and the last class of this course from my side will be tomorrow, same time. Okay, not next Monday. It will be tomorrow, 6 to 8 p.m. next class, and that will be the 12th and last class of this session for me. Okay, so last class there were some. So we studied magnetic circuits from where we went to single phase transformers. There were some simple one or two questions of single phase transformers. Here we will have several questions on single phase transformers, more higher concepts, and we will have some simple questions of three phase induction machines. Next week we will have uh, questions on DC machine. Means next week means not next week, tomorrow, and some questions on induction machine, three phase induction machine. Okay, so first, as usual, I will ask you if you have any doubt from this week or last or any other week's lectures. Any doubt or any question? Okay, if not,
No, sir.
then we will start. Yeah, go ahead. No, okay. We'll start. You can stop me anywhere if you want to ask something. So the first questions are first few questions are about transformer, and some two three questions are there on induction motor. The first question says two single phase transformers A and B are supplied from 215 volt 50 hertz source and 430 volt 60 hertz source respectively. The cross section area of transformer A and transformer B are given, and they operate at the same flux density. If the total number of turns of transformer B is 300, find the total number of turns of transformer A. Now you see one thing here. Mm, this flux density is determined by the material. This peak flux density, mm, peak flux density or RMS. They did not mention it here. Anyway, we do not need it also. Uh, that is determined by the material. I think what they have given here is not the peak. Just a minute, I will just check one thing. It is not required for this question anyway, because 0.7 Tesla flux density for a power transformer is much less. Anyway, fine. So, okay, so we'll have to find out the relation between supply voltage, flux density, and frequency. Maybe frequency, we'll see. Now we'll start from Faraday's law of mm, induction, which gives V equals d psi dt. See, I am writing lowercase v. That means I am talking about mm, instantaneous quantities. Now, the supply voltage is sinusoidal, so definitely the flux will also be sinusoidal. So let us take the instantaneous value of flux linkage psi to be something as psi max sine omega t. Now, if you put it here, it is psi max sine omega t. Then differentiate. What you will get is um, omega psi max mm, sine, sorry, cos omega t, cos omega t. Now, see, psi is flux linkage. Flux linkage is number of turns times flux. So here I can write omega will be here as usual, omega n phi max cos omega t. Again, phi is flux, which is flux density times area of core. So it is omega n, area of core I write as say AC, times B max, peak flux density in the core, cos omega t. Okay, so you can see from here that this is the instantaneous value of the supply voltage. It's a sinusoidal supply. Now, from here you can say that the peak voltage Vm, peak supply voltage, is omega n AC Bm. Okay. Now we have been asked to find out turns, number of turns of transformer A. Total number of turns, actually it's maybe one side, one either primary or secondary side. Anyway, there is nothing called primary or secondary side of a transformer. It's high voltage and low voltage side. Okay, so try not to use primary and secondary side. So now if we write this in terms of ratio of these two transformers 1 and 2, what we can write is Vm1 by Vm2 equals omega 1 n 1 AC1. Bm is same for both, omega 2 n2 AC2 Bm. Now see, we are in the question, the values that those are given, they are definitely RMS, not peak values, but since we are finding out the ratios, we need not convert them. We can because if you are going to convert it to multiply with the same factor, so we can write like this: 215 by Vm2 is 430 equal to, again, omega is in radian per second, but since we are finding out ratio, we'll simply write whatever there in hertz. 50 times n1 we have to find out. B is 300, they have given. N1 into area of core 1 is 1.5 centimeters squared. Again, this is not in SI, but we need not convert. Bm is same for both. I'm not writing anymore. Divided by 60 times transformer B has 300 times 0.75. Now if you solve this, you will get N1 as 360. Any doubt in this question?
No, sir. No.
Okay, we'll go to the next question. Okay, negative voltage regulation of for a single phase transformer can be obtained. What is negative voltage regulation? See, the um, voltage regulation is given by this. If you see that, do you know what is voltage regulation? What is voltage regulation of a transformer? Yes or no? At least. So it's a fuzzy state. You may know, you may not know. At least to me. So voltage regulation is, say you have a transformer. This is, say, one end. Let us call this, say, primary. The other end. Now you connect a supply voltage source to this. Okay, and this is a non-ideal transformer. It has non-idealities involved. Now, once you supply this, you get some voltage, which is the induced EMF in the secondary. Now, what happens is, once you load this, since this series impedance, they are carrying some current, the voltage drops. Basically, E2 comes here. E2 does not come here. E2 comes here. E2 comes here. and what you get here is V2. So there is, when there is no load, what you get is V2 equals E2, but when there is load, V2 does no longer remain equal to E2, and there is a change in voltage. That change is called voltage regulation for that definite load. It depends on the load power factor, the impedance of the load, and everything. Now, if you look at this equation, this you can see it's a positive equation. The value will come as positive, but um, this one is derived. If you see the derivation of this, the geometrical derivation, it is the drawings are all for the phasors are drawn for lagging power factor. So if the voltage regulation is positive, that means if E2 is less than V2, that means the voltage regulation is positive. Means you load the transformer, the voltage drops. That is called a positive voltage regulation. Now this thing happens for R loads and L loads always. Only for the cases, means if you see E2 is less than V2, that means you had some voltage at the terminal, you load the transformer and the voltage increases, which is what to say, counterintuitive. Generally what we think is once we load the voltage reduces, but you load the transformer and see that the voltage increases. That means a negative voltage regulation. That can happen only in the case of a capacitive load, that is leading power factor. Now here remember one thing, that capacitive load does not necessarily mean that you will have a leading power factor. Beyond a certain value, you will have leading power factor. That depends on the power factor of the load. Okay. If it is lightly capacitive, you will not get leading negative voltage regulation. Okay, so here it is leading power factor. Any doubt? Okay. A 220 volt, 110, 220 volt by 110 volt, 1 kVA, 50 hertz, two winding single phase transformer is to be used as an auto transformer. Auto transformer or variac, we also call it variac. That is simple regulator, voltage regulator, not the regulator that you see for your fans, but the older regulators you may say to some extent. So it's to be used as an auto transformer to supply power at 110 volt from 330 volt. So let us first draw the transformer how it was before we connected it as a auto transformer. It was a simple 220 volt to 110 volt transformer. Sorry. It was like this. Say this is the 220 volt side. Say this is the 220 volt side, or I will write it there. 220 volt side, and is the 110 volt side. So this was the single phase transformer. Now this has to be used as an auto transformer. So before we use it as an auto transformer, what we have to do is we have to reconnect. We have to make some connection. So what we need the 110 volt. So here this is gonna be the input of the auto transformer. On the other hand, it should be 330 volts. So the 110 volt and 330 volt should be connected in series. Now here is a catch. Say the 110 volt is like this, whereas the 210 volt, the 220 volt, how we are measuring, it's like this. It has to be connected like this. Then only they are in series. If you connect the other way, it will become subtractive. So how to know which terminal to connect where? So for that, what we have to know is the dot polarity of the transformer. It is either painted on the transformer, or if it is not painted, then what you have to do is you have to do a test. There are, oh, I forgot the name of the test. Only the DC kick test, that is not very popular. what we do is we add the transformers like this and then find out the voltage difference between the others. Anyway, so in that way we can find out the polarity of the transformers. Once you know the polarity, now what we can do is, see, it should be connected like this if it has to be in series, additive series has to be like this. So the dot of one should go to the under of the other. So the extra connection that you have to make in order to make this an auto transformer is this, right? Now where is our output? Where is our output? See, this one starts from here, so this will be output. Here we will get 330 volt from this terminal. If you say, if I name them, say terminal A, B, C, if I name them, then from terminal B, if you see, voltage AB is 110 volt, and from here if you see, from B, if you go in this path, sorry, then you have 110 plus 220, 330 volt. So this is the connection if you have to use the transformer, single phase transformer, as an auto transformer. Now once you have this connection, now the question is, determine the kVA output of the auto transformer. Okay, now kVA output means we have changed the connection, but we cannot cross the current and voltage limits of the transformer. That is, if this winding, say, if this winding is rated for I ampere, we cannot increase that value. The transformer will burn. In auto transformer operation also, we have to make sure that it does not cross the value I ampere. And if this is I, then definitely this will also be I by 2, because the voltage is twice. The current will be halved. And the arrow direction is important here. I did it from the dot polarity we discussed last class, the dot polarity. Now, sorry. Now here I current is flowing, and if you follow this I by 2, it will come up here, just in series I by 2. So basically, the current that the transformer can draw now at rated condition is 3I by 2. So previously the transformer could draw how much? The previous kVA rating as a transformer, single phase transformer, was 110 times I. Now at the terminal we can see that the transformer can draw 110 times 3I by 2. So definitely the kVA has now becomes 1.5 times. So this will be the answer.
Sir, I can't able to understand the connection.
Okay. Okay, I'll show you one by one. Could you understand this part? That I have to connect like this.
Minus to plus.
Before that, you tell me. See, this is an AC voltage source. Say I call it V sin omega t. Its value, instantaneous value. You will see in the books and everywhere there are plus and minus signs. In DC, I understand this terminal is at higher volt potential than this. But in AC, what is the point of putting plus and minus? The polarity is alternating. Then what's the point of saying the one terminal as plus, other terminal as minus? Deepak or Rishi, anyone can answer.
Sir, please tell again.
Can you please be louder? I can't hear you.
Sir, please tell again what you said before.
What I'm saying is, what is the point of giving the plus minus polarity in an AC voltage source. The voltage is anyway alternating. Sometimes this terminal is plus, sometimes this terminal is minus. But still we give plus and minus. What is the meaning of this? Or is it as at all necessary? For
Because
DC
the
voltage source, we
connection is
understand. Yeah.
alternating. Because if
Louder, louder. I
the
can't hear you, Deepak. Louder.
because if the current is alternating.
Yes. So if it is alternating, then sometime it is plus here, minus here. Next moment it is minus here, plus here. Again plus here, minus here. Then what's the point of putting plus and minus? You will see everywhere in AC source they will put this plus and minus sign. Rishi. Okay, so this is something that I discussed for more than 10 minutes in the very first class. I told you these are very important. Anyway, so although it is alternating, but if you see here, suppose this is the sinusoid voltage. Okay, say I call this, say we take 10 volt peak, 10 minus 10 volt peak. Okay, this is V. Now, if certain time, say at certain time here, if you measure what you are getting, you are getting some positive voltage. Now if I do not draw the positive negative here, how would I know which point is at higher potential? Once I put this plus and minus, the meaning of this plus and minus means the voltage of terminal A with respect to terminal B is plotted here. That means if it is positive, voltage A is at higher potential. If some other instant, if it is negative, the voltage of or the potential of point A is at a lower potential of point B. This is the whole meaning of putting this plus and minus. Now, if you have 110 here, if you have 220 here, and if you have to make a 330 out of it, this is the connection that you have to make. You cannot connect it here. That will give you a subtractive voltage. Is this diagram clear? This one. That if I want,
Then sir, when we connect a terminal to primary source last terminal, then how come 110 volt and
no, no, Deepak, this
then
top right corner diagram, can you understand? Do you understand that the connection has to be made like this if I want 330 volt? I cannot connect this terminal to this terminal.
yes, not connect.
Clear? Is it? Could you understand?
Yes, sir.
Okay. Now look at this one. Dot convention we discussed last week. So what does this dot mean? It means that if I measure the voltage here V1 and the voltage here V2, they are in phase. If this is V1, V2 should be here like this. Which means if you want to add the voltages and if you have dots and dots here, they have to be connected like this. Now you compare this diagram with the connection of the auto transformer that I have shown. Is it clear, Deepak?
Yes, sir.
Okay. Any more doubt, or we'll go to the next question?
No, sir.
All right. So leakage voltage regulation question. 100 kVA, 12.66 kV by 440 volt, 50 hertz single phase transformer has 18% impedance. The leakage resistance referred to the low voltage side is this much. Find the percentage voltage regulation of the transformer when it is connected to 0.6 leading power factor load. All right. So the leakage resistance. I don't know what is leak. See, there is nothing called leakage resistance. It is the winding resistance. Okay. Leakage inductance and winding resistance. They are together called leakage impedance. That is true. But there is nothing called leakage resistance. Anyway, so it has 18% impedance. So we have to find out the impedance basically first. Now the impedance is given in percentage. How is that possible? Any idea, Deepak?
No, sir.
So this is called per unit resistance. Per unitization is to give you an idea about the general.
Yes, yes. Per unit, I read in power system.
So you studied power transmission power system. Okay, there also it is used a lot. Mm. So basically, it is to give you an idea of, in general, idea of the impedance values, I should say, because if you look at a, say, transformer of completely different ratings, their impedance values, absolute values will be different. But per unitized, if you see, they will be more or less comparable. Okay. Now, okay, so what we have to do is we have been given the per unitized impedance. From here, you have to find out the actual value of the impedance. So for that, we have to first find out the rated current, which is 100 kVA by, I'm doing it at the low voltage side. So 227.27 ampere. This much is the rated current. Now from here, what we can find out is the base value. To per unitize, you need some base. So the base value of the impedance is 440, the voltage by current. 227.27 ohm, which is 1.936 ohm. Now, once you know this Z base, from here you can find out the total leakage reactance. All of this we are doing at the low voltage side. Okay. The per unit impedance does not change whether you calculate it at the low voltage or high voltage side. In high voltage side also, if you refer all the impedance to the high voltage side and then calculate the per unit impedance, you will get the same thing. Same 18% you will get. So the leakage impedance, it is the 18% of the base. So 1.936 times 0.18. which gives us 0.348 ohm. So this is the leakage impedance. Now the resistance on the secondary side is given as 0.3 ohm. So from here we can find out the leakage reactance, which is, square root of z squared minus r squared. So 0.3485 squared minus 0.3 squared, square root of that gives us 0.1773 ohm. Now, once we have this, we have to find out the percentage voltage regulation of the transformer when it is connected to 0.6 leading power factor load. But what percentage of load? What percentage of load? They did not mention. We will take it as full load. Okay. So now if I find out E2 minus V2, which is R2I2 cos theta 2 plus X2I2 sin theta 2. Now if you put values, R2 is 0.3 times I2. It's rated, we have assumed to be rated, so we will take this rated value that we have calculated. So 227.27 times cos theta is 0.6. It is leading power factor. I told you that this one is calculated for um, lagging power factor. So what we have to do is we have to put a negative here, because this one is calculated for lagging. We are question is given leading, so basically we are just replacing theta 2 with minus theta 2. Cos theta 2 does not change, sin theta 2 becomes minus sin theta 2. That's why the minus comes here only. So minus x2 is 0.1773 times I2, once again 2 times 227.27 times 0.8. If cos theta is 0.6, sin theta will be 0.8. Now if you calculate this, it will be 0.3 times 0.6 minus 0.1773 times 0.8, which gives us a positive value, 8.67 volt. So positive value means you can just look at one thing here. E2 is greater than V2. So you see, although this is a leading power factor load, um, after you load the machine, load the transformer, the voltage drops. So it's not necessary that leading power factor will cause a rise in voltage. Now, if it is 8.67 volts, since we calculated from the low voltage end, we can find out per unit voltage regulation from the low voltage end only. 8.67 by 440, which will give 1.97% voltage regulation for this one. Any question?
No, sir.
Is she trying to say something? Okay. So we will look into this question. Open circuit test, short circuit test data of a transformer is given, and some questions are asked. Actually, For the same transformer, where open circuit and short circuit test results are given, there are three questions, three back-to-back questions. Same data are given in all the three questions. So what we will do is, although we will not need in the first question, we would still uh, find out all possible data that we can from the open circuit and short circuit test data. Then we will use it wherever we need. Okay. So open circuit and short circuit test of transformer and induction motor also are done to find out the equivalent circuit parameters. So the equivalent circuit of a transformer looks like this. First you have series. I will draw the whole thing referred to one side. I hope you know this. Now, one thing I wanted to tell you is that in many books you will see that as the equivalent circuit of the transformer, they will draw only this. The transformer that they will draw is this, the non-ideal transformer. But they will just simply call this as the equivalent circuit of the transformer. That is not true. This one only contains the non-idealities of the transformer. After this, there is the ideal transformer. This one is the ideal transformer. So the equivalent, so this network followed by the ideal transformer, this whole things constitutes the equivalent circuit of the transformer. Okay. All right. Now we will look into the questions. First, we will see what all we can find from the open circuit test. Now, open circuit test is always done at the low voltage side, because the objective of open circuit test is to find out the core loss. Now, core loss depends on the voltage and the frequency. Now, since we have to find out the core loss, we have to, what we'll do is we will send it to full voltage. Why to full voltage? Because that is where the operating point of the transformer lies. So open circuit test is done at full voltage. Now, since it is done at full voltage, it is done at the low voltage side. You need not have or might not have the facility to develop or generate that much high voltage on the that that is there on the high voltage side of the transformer. Say for example, in this case, if your facility has 110-volt AC source, you can do an open circuit test. You can do from the high voltage end also, but that would require a presence of a 440-volt supply. You may not have it. Okay, but you can do, if you have facility, you can do. That will not give you some different answers. Only thing, it will give you answers refer to the other side. Okay. What all? All right. Now this is done at the high voltage side. Now what happens is, since this is open circuited, the transformer only the transformer draws very small amount of current, because there is no current load here. So the current in this loop is zero. So the only current that the transformer draws is magnetizing current. So the drop in this, the drop, sorry, the drop in this impedance can be neglected in open circuit test. If we do so, then the transformer equivalent circuit in the open circuit test becomes like this. It simply becomes this. Since the value of current is very less, the drop across this impedance, the loss in the leakage can be neglected. The transformer is operating at no load. Now we have only this. We have the RC and XC, which is the magnetizing branch of the transformer. Now we have applied 110 volt and got this much current, this much power. From here we have to find out RC and XC. Now you see the only power consuming element here is the RC, and the voltage across it is 110 volt. So the whole power is definitely consumed by RC. So from here we can find out RC, the magnetizing branch, or RC actually shows the core loss component. RC is V squared by P, which is 110 squared by 10 watt. If you do that, I did it in the morning, you will get 0.1555 ohm. This. Now we have to find XC. So XC doesn't consume any power, but if this is no, sorry, this is not RC. RC cannot be this small, right? I wrote it the other value of R. This V square by P, it will come 1210 ohm. Magnetizing branch resistance and inductance are very large, otherwise they will almost short circuit the supply. 0 ohm. Now if it is 1210 ohm, then from here we have to find out XC. How to find out? See, it's a parallel circuit. So if this is the voltage, supply voltage V, then this is the current drawn by RC here, and this is the current drawn by XC. And this is the resultant that we are measuring at the terminal. So this value is 0.1286 ampere, and since we know the value of RC, we can find out the current flowing through it, which is around 0.09 ampere. Now by Pythagoras theorem you can find out what is the current through XC or IX. IX will come out as 0.9095. Now you know the voltage across XC, you know the current flowing through IX, as flowing through XC, that is IX. So from here you can find out XC by Ohm's law, which is 1209 ohm. So the question, the magnetizing reactance refer to the low voltage side in kilo ohm is this. This is the closest one. Any doubt here? Okay. Now we'll find out what the short circuit test will give us. Then we'll go to the next problem. Now the short circuit test is done at the high voltage side. Why? The short circuit test is done to find out the thermal test, or the thermal or the temperature rise or ohmic loss of the transformer. So you have to make sure that full load current flows through the transformer. Once again, you can do it from the low voltage side, but energy conservation law says that the low voltage side will have high amount of current, and since the transformer is short circuited at one end, the voltage rise, or in other words, to send rated current from the other terminal, we will not require the full voltage since it is not loaded, it is short circuited. But since it is short circuited, it will carry the full current.
Sir, in this
Now,
question, how you find the IR and IX value? And
Deepak, louder.
sir, in this question, how we find IR and IX value?
Could you understand how we find out RC value?
No, sir, RC value also not understand where it comes.
Okay, look at the data here, open circuit test data. 110 volt is applied, and it is found that 10-watt power is being consumed by the transformer, and this much current is being drawn by the transformer. And this one is the equivalent circuit at open circuit test. Can you understand why this is the equivalent circuit for open circuit test? Why can I neglect the other impedances?
Because secondary side is
No, no, have
open.
you understood? That's if you have, that's fine.
Okay.
Have you
Second
understood? Yes or no?
secondary side is open.
Then
Then secondary terms neglected. Uh, R2 X2 V2.
so this one is neglected. I understand. What about this one? There is current flowing through this.
Current will flow only on primary side.
Yes, so there will be drop in the primary leakage impedance, right? But that is also being neglected in the open circuit test. Why? How can I do that?
Sir, please once more.
Because the current that is being drawn at open circuit test is very less. Because the transformer is not supplying any load. So the only current that it is drawing from the supply is to magnetize the core, which is designed to be very less in power transformers. So since this current is very less, this supply voltage here, it is dropping at two places. One is the leakage impedance of the primary or the low voltage side. Other one is the magnetizing branch. Since the low voltage side leakage impedance drop is very less, we can ignore it. The magnetizing impedances are much higher compared to the leakage impedance. That's why we can ignore. Now we have this circuit. We know that when we apply 110 volt in this circuit draws this much current and consumes 10 watt of power. Now, which one is the only element that can consume power here in this circuit?
RC
Are you sure?
and RC and XC both consume power.
XC will consume power.
Sorry, sir, store power. Uh,
No, but store power, this is 10 watt. This is active power that is continuously being consumed. Does an inductor store energy in AC circuit?
in AC circuit, store energy inductor.
What are you saying? I can't understand. Doesn't, say for a DC circuit at steady state, we can say that this inductor is holding this much energy. For an AC circuit at steady state, can you say something like that?
Inductor store energy.
Can you say something like that?
In steady state, I have less idea.
You have more idea in transient.
In transient, inductor stored energy T is equal to 0 plus and T is equal to 0 minus timing duration.
I have no idea what you were saying. Anyway, uh, the inductor doesn't consume any power, so the 10-watt power is consumed by the resistance only, the magnetizing branch resistance, which basically represents the core loss of the transformer. Now, if it is 10 watt, and what is the voltage across this resistance RC? What is the voltage?
110 volt across RC.
Are you sure?
Uh,
There is
yes,
AC also in parallel.
yes,
So if you know the energy consumed by a resistor, and if you know the voltage across it, can you not find out the value of the resistor?
yes.
So this is the formula for that: P equals V squared by RC, V squared by R.
I understand how come RC value.
Okay, now you know the voltage across RC, you know the voltage, you know the value of RC, so you know the current through the resistance, right? Resistor.
Current through the resistor. Oh, KVL. KCL. By doing KCL, we can find
Do you need
like
to do KCL to find the
sorry,
current in RC?
no, no, sir, KVL, KVL.
Okay. Can you find out the current through RC?
P is equal to I square RC. Say
Why I squared RC? You know the value of the resistance. You know the voltage across it. Why do you have to find out the power in the resistance to find out the current?
sorry, sir. I
It's
is
simply
equal
this
to
voltage by resistance.
yes, sir. Voltage by resistance.
Now, do you understand this phasor diagram?
Yes, because two component magnetizing uh, and active component had 90-degree angle and
Should Ix lead V or lag V?
lag.
Why lag? Because it is an inductor. Inductor draws lagging current.
Yes, sir.
Now, if you have IR and IX, and if you apply KCL here, by vector addition, you will get IL.
Yes, yes, sir.
Now,
I
can we apply Pythagoras theorem here? Now we know the values of IR and IL. From there, we can find out the value of IX. Now, what is the voltage across XC, the magnetizing inductance?
110 volt.
You're asking or answering?
No sir, I answering 110 volt होगा XC के क्रॉस वोल्टेज.
What does this circuit tell you? What should be the voltage across XC?
In in parallel voltage is same.
Same, so 110 volts. So you know the current through XC, you know the voltage across XC. From there, you can find out the value of XC. Deepak, am I audible?
Yes sir, yes sir.
Okay. So is it clear? Is XC clear?
Yes yes sir.
Sure.
Uh,
Look at this equation. This one. You could understand this equation? Any doubt here?
Where is the point?
Louder, louder. I can't hear you.
Where is the point?
This
IL
on the right
square
hand side
into.
equation. Yes.
Yes yes I understand.
So from the in this equation, this is known to us. This is known to us. We can find out Ix.
Yes yes. XC is find. XC can find
Okay, X is you
100
can find.
110 divided by point 90. But,
Okay. So that's all we can find out from open circuit test. Open circuit test gives us the core loss, that is the information about the magnetizing branch of the transformer. Now, short circuit test, we are short circuiting the other side. So so you do not need rated voltage for the rated current to flow, since the other side is short circuited. Only a limited small amount of voltage can make the short circuit current flow. Now, since here also the same thing, if you do the short circuit test at the low voltage end, the source which you are using to do the test must have high current rating, because low voltage side current rating is high. But if you do it at the high voltage end, you will the source that you are using to do the test can have low current rating. Once again, you can do it from any side, but the practical choice is to do it from the high voltage end. So the short circuit test is done from the high voltage end. If nothing is mentioned, it is done at the high voltage end. Okay. Now all these data that we got here in the open circuit, they are at the low voltage side. Okay. Low voltage
sir,
side.
110 डिवाइड बाई 0.9095 XC की वैल्यू फाइंड करने के लिए करना था या फिर आपने
I can't hear you,
नॉर्मल.
Deepak. You move the microphone close to your mouth.
सर ये था कि XC की वैल्यू फाइंड करने के लिए 110 डिवाइड बाई 0.905 करना था ना सर.
9095.
बिकॉज IX तो 0.9095 है, तो उससे तो
How much do you get?
120 120.9.
Okay, wait. I think I have. Resistance value we got this much, then 110 by, I think I have put the decimal at the wrong place. It is 0.09, it is correct. Now if I use 0.1286 squared minus 0.09 squared, yeah, Ix is square root of 0.1286 squared minus 0.09 squared, which will give you 0.0919 ampere. That is someone 1197 ohm, not this. Still, this is the closest. Working now?
Yes, sir, I understand.
Okay. So now we will do the short circuit test calculation. So it is done from the high voltage side. And since very low amount of voltage is enough to send the short circuit current, the current through the magnetizing branch can now be ignored, because their current depends on how much voltage you are applying, or in other words, core loss depends on how much voltage you are applying. And since the voltage supplied is very low, core loss can be ignored. So this is the equivalent circuit for the short circuit test. Now you give 20 volt. One thing here is short circuit test does not give you the values of the resistance and impedance separately of low voltage and high voltage side. That is not possible. So what we take is we take half of, okay, we divide them into half, but that does not change our, how to say, calculation of losses. Now it is saying 20 volt, when we apply we get 10.3 ampere, 16.50 watt. 10.3 ampere, 16.50 watt. Now this R and X are here. Definitely this R is causing this much of power loss. So 10.3 square times R is 16.50. Just verify that I am writing the values correct. R should be this. Is it correct? I think you should understand this. There is nothing difficult here. Tell me if there is any doubt. It's very straightforward. Simplest AC circuit.
No doubt.
Okay. So in this way, we find out R and X also. But remember that the data that we got in the previous calculation are from the low voltage end. This one we got from the high voltage end. So from here, if you are trying to draw equivalent circuit like this one, like the one I have drawn here, you have to uh, refer the impedances to the other side, any one of them. Maybe you can refer this to the low voltage end and draw. Okay. Now look in the next question. See why I did all this calculation, because the same data is given, and now the question is find the KVA loading at which the transformer will give maximum efficiency. Now a transformer gives maximum efficiency when the copper loss becomes equal to the core loss. Core loss I will write as PFE, iron loss. Now it's customary that we always operate the transformer at a constant supply voltage and frequency does not change. So the core loss of the transformer can be taken to be practically constant throughout the operation. So, and that is also the loss that we get in open circuit test. So this is the rated core loss of the transformer. Rated core loss means core loss at rated condition of the transformer. So we have to find out at what loading condition our copper loss also becomes 10 watt. So we will do it in the secondary side. Okay. So, sorry, not secondary side, high voltage side. High voltage side, our total resistance, this is total resistance at high voltage side we got from the short circuit test, is 0.1555 ohm. And at certain loading condition, the copper loss is 10 watt. Then how much current is flowing at that loading condition? It is simply this, which is 10 by 0.1555. We are getting some 8.02 ohm, sorry, ampere. So when the secondary side is carrying this much current, um, the copper loss becomes equal to core loss. Now you see here one thing, we don't care about the power factor here because resistance does not understand the winding resistance, how much power at what power factor is being delivered. All it understands is the RMS current flowing through it, and that would dictate the loss in the resistance. So if this can be a perfectly, yeah, this can be a purely inductive load also, but this much current is flowing at the high voltage end, high voltage side, that we know. Now if that is the current flowing at the high voltage end, high voltage is 440 volt voltage, now we can find out the kVA. It's simply 440 times 8.02 ampere by
So R is equal
1000. Deepak, louder.
सर R is equal to 0.155 किसको किससे डिवाइड करने पर आ रहा है?
We found that from the short circuit test.
ऐसे।
Okay.
But but we work on open circuit firstly. Open circuit का तो resistance अलग था.
Open circuit resistance. Okay, let me draw once again. This is the equivalent circuit of the transformer. I am drawing the even simpler one. you can think like this. See, a transformer is made of two things primarily. This is the core, this is the core, and this is the winding. Okay, so these are the two primary components of a transformer. Now all the losses in transformer happen at these two places, at the core and in the windings. The core loss is represented here in this branch. So you can say in the equivalent circuit of the transformer, this branch, this parallel branch, that represents the core, and this branch or this series impedance, this represents the winding. The loss happening in the parallel branch is the core loss. This gives you the core loss, and the loss happening here, that gives you the copper loss in the winding. Here we equated core loss and copper loss because that is the condition for maximum efficiency of a transformer. Now core loss is constant because core loss, among other things, is a function of maximum flux density, which is in turn a function of voltage. So I will write voltage and frequency. It's a function of voltage and frequency. Now during the operating condition, the voltage and frequency does not change. So core loss remains practically constant. So whatever core loss you got during the open circuit test, that will remain constant. So 10 watt core loss will remain constant. Now at that loading condition where the copper loss will be 10 watt, we will get the maximum efficiency from the transformer. Now this resistance is the copper loss resistance. That's why I took this one, the short circuit test resistance. Is it clear now?
Yes, sir, clear.
Okay. Same question. Thing is, find the percentage efficiency of the transformer at 90% of full load, 0.6 lagging power factor. Okay, 90% full load, 0.6 lagging power factor. Just a minute, let me think a little bit on this. Okay, so when we say that 90% full load, it means the transformer is now carrying 90% of its rated current. Okay, it is now carrying 90% of its rated current. I will draw the equivalent circuit from the high voltage end. We found out the magnetizing branch impedances from the low voltage end, but we need not transfer them because at the end all we have to find out is the loss. Okay, so what is the rated current at the high voltage end? At the high voltage side, the rated current is 5 kilovolt ampere by 440 volt, which would give you 11.36 ampere I rated. So the load current that is flowing now is 90% of this, which is 10.23 ampere. Okay. Now this resistance we know. So we can find out the, so this is the current I load flowing. Or I should not say I load, let us call this I source because load will be there. Okay. So 90% of the rated current is flowing I source. Now we can find out the total loss. Total loss is copper loss plus core loss. Core loss never changes, always the same if and as long as the voltage is kept constant and the frequency also. Now you have copper loss of this much and core loss as usual, which is 26.27 watt. Okay, so this is the total loss. Now we have to find out the input power. Now input current is given. This is 0.6 lagging power factor. They have not mentioned whether it is a load power factor or something. Let's take this as here. The power factor here is just as 0.6 lagging. Now if so, then power input, this is power loss, power input is 440 times 10.23 times 0.6. It's around 2700.62 watt. You see, the transformer is operating at 90% of its load, but since the power factor is so small, the active power is around 50% of the kVA rating. Now from here we can find out efficiency. Efficiency is output power by input power. Output power can also be called as input power minus loss. So what we have is 1 minus loss by input power. So 1 minus 26.27 by 2700.6. It was 7.2, I think. Yeah. Anyway, that would change much. .99 something is coming. So it's not matching any between none of them. Tell me if there is a doubt in the solution. Any doubt in the solution? If not, we'll go to the next question. This one is quite a long question. Do you have something else? So many questions. Okay, anyway, we'll do this. Yeah, Deepak, want to say something?
Okay.
All right, so this is something called all-day efficiency of a transformer. Now, all-day efficiency of means all efficiency is not relevant for any transformer. It is relevant only for the distribution transformers. It is the transformers that you have um, at in your locality by the roadside on the electric poles. Those transformers are distribution transformers. It is applicable for them only. Why so? You can always calculate all efficiency for any transformers, but the power transformers are in general always operating at the peak of their load. That as a result, the power transformers are always designed so that they always operate close to their peak efficiency point. But the distribution transformer cannot operate, or they do not operate close to the rated load always, because it's a locality, it's supplying a locality. Daytime maybe some appliances are on but illumination load is off. Nighttime more illumination load, maybe after 9-10 p.m. ACs are on. So the power fluctuates a lot for a distribution transformer. That's why it is a distribution transformers are developed or designed such that the old efficiency, that is the total energy output in 24 hours by the total energy input in 24 hours, this is maximized. This is maximized for a distribution transformer. You cannot maximize the efficiency at one point. That is not an optimum solution for a distribution transformer. Okay. Now we have to find out. So the one kind of load profile is given. For 6 hours how much, for 4 hours how much. We have to find out the efficiency. So basically you have to find out the losses. You have to find out the losses. So let us see. Yeah, the loss is also given in a cryptic fashion. It is given like this. It has maximum efficiency of this much at 5 kVA unity power factor. Now, the transformer is rated for 5 kilovolt ampere. It is unity power factor. So at maximum efficiency, so when it is maximum efficiency, the output power is 5000 watt. Okay, why watt? Because it's unity power factor. Efficiency is given. So from here we can find out input. Input is what? Output by efficiency, which is 5028 watt. Now from here you can find out the loss, input minus output. You will get something, if you consider the decimals also, something like 28.2 watt. Now since this is the maximum efficiency, so at this case copper loss equals core loss, they're equal, so this by 2, 14.1 watt. Now as I said that copper loss is a constant. It is a constant. Whereas this core loss, sorry, what did I say? Core loss is constant. Since the voltage and frequency are constant. We discussed here also the previous problem. Whereas the copper loss, it's proportional to I squared, the load current squared. Now we have the load profile. So for all the cases, we have to find out the losses, total loss. Okay. So we will divide it in 3 sectors. Say sector 1, 2, sorry. For sector 1, for 6 hours, what happens? 1 kilowatt power. So mm, it says it is loaded as follows: 1 kilowatt. So output is 1 kilowatt at 0.6 power factor. Just a minute. Yeah. So output is it's kilowatt only. So 1000 watt. What about the loss? Core loss is constant at 14.1. What about the copper loss? So try to understand this. If you don't understand, tell me. 14.1. If the load is 5 kilowatt, the copper loss is 14.1. So let us talk about the current. What is the current when the load is uh, 1 kilowatt? So during 5 kilowatt, the current was something. Now, if the load becomes now 1 kilowatt, the current becomes 1/5. The current becomes 1/5. It's 1 kilowatt by 5 kilowatt times this squared. Similarly, for sector 2, tell me if you don't understand this. Wait, am I doing something wrong here?
सर मल्टीप्लाई 1/5 स्क्वायर कैसे हो गया?
Deepak, I can't hear you until you move the mic closer to your mouth.
सर 14 मल्टीप्लाई 1/5 होल स्क्वायर कैसे, ये 1/5 कैसे आ गया?
Because 14.1 watt was the copper loss when the load was 5 kilowatt.
Yes.
Now the load is 1 kilowatt. So the current is 1/5. So if the current is 1/5, then the loss will be 1/5 squared.
Yes. Yes, sir. Okay, sir. Okay. Understand, sir.
No, but here I think I have done a mistake. Just a minute. Yes, I have done a mistake here. See, I will show this calculation for one and you will do it for the others. Okay, not now, later. But notice this very carefully. I will show it step by step. I am taking the sector 1. What is the output? Output is 1 kilowatt, 0.6 power factor. Okay. But who decides the current in the transformer? Not, it's not the kilowatt that decides the current. The kVA decides the current. So during this time, the output active power is this much, but the apparent power or the kVA, it is 1 by 0.6. So this will decide the current because the reactive power is also flowing, right? So for 6 hours, this much kVA is there. Whereas we got 14.1 watt of copper loss when there was 5 kVA load. So now the current is 5 by 3 by 3, that is sorry, 5 by 3 by 5, that is 1/3 of this loading. So during 5 kVA, whatever current was there, during 5 by 3 kVA, the current is 1/3. So if the current is 1/3, the load is 14.1 core loss plus 14.1 times 1 by 9. If you do this and find out the input power, you will get 1016 watt. Is it clear? The current is decided by the kVA, not by the kilowatt. Since now the kVA is 1/3, so the current is also 1/3. Similarly, you see for the 4 hours in the next section, next case, it's 5 kilowatt at 0 point in power factor. Notice one thing, the transformer is rated for 5 kVA and now the load is 5 kilowatt, very fine, but the power factor is 0.8, it's not a unity power factor. So basically the transformer is now supplying more kVA than rated. Although it is supplying 5 kilowatt, it is overloaded because the power factor is not unity. So during this time, you can say apparent power is 5 by 0.8 kVA. So at this time, the current in the transformer will be how much? 5 by 0.8, which we are comparing with 5. So 1 by 0.8, that is 1.25 times the rated current. The transformer is 25% overloaded. So this will be 14.1 plus 14.1 times 1.25 squared. This will give you, now what we are doing is this plus this is this. So this is 5036 watt input. Similarly for 14 hours, how much is the data? 4 kilowatt, 0.95 power factor, same. I'm not doing it once again. It will be 14.1 plus 0.1 times 0.7, which will give you 4024. Right? Now you have data for all whole 24 hours. So you can find out the total energy output by total energy input. That will give you the all day efficiency of the transformer. So the total energy output is 6 for 6 hours. It is this much watt. For 4 hours, this much, and for 14 hours, this much. The total energy output divided by the total energy input, 1016 again for 6 hours plus for 4 hours plus for 14 hours. If you do this, the all day efficiency is basically average efficiency, nothing else. That total over a day, average over a day, that will give you something around 99.34% efficiency. So you can understand that throughout the day. So if you see, so if you see, say for this 6 hours, the efficiency was 98.4%. for this 4 hours. This is not required. This I am telling you only to give you some idea. It was more 99.2. For this 14 hours, the efficiency was 99.4. So the energy, so the efficiency keeps on varying throughout the day. What we are concerned of in case of distribution transformer is the all day efficiency, the average efficiency that should be maximized. Okay, is it clear?
Yes, sir.
All right, we'll go to this question. The same auto transformer question. I'll quickly copy this diagram. The same question, if you see the same transformer they're talking about. Read the question. Now the transformer, before it was connected as an auto transformer, before it was means it when it was being used as a regular transformer, it had a 92% efficiency at full load, unit power factor. Now it is reconnected like this. Its efficiency at its new rated load will be how much? Now see, when we found out how much is the new kVA of the transformer, we told one thing, that the voltage rating and the current rating of the transformer, that is not crossed. That is, if you look from the winding point of view, even if you are connecting the transformer as an auto transformer, the windings still see the rated currents flowing through them and the rated voltage across them. That is the load, that is the loss does not change. So whether the transformer is used as a regular transformer or an auto transformer, the total loss in the transformer is the same when it is being operated at full load. Is that clear?
Yes, sir.
Now, if you write when it was operating as a regular transformer, what is efficiency? Efficiency is output by input. Output is input minus loss. Okay. Now this is given. So this we know, right? For the regular transformer. Now what happens when we are operating it as auto transformer? The input power changes. We saw there that for regular transformer input power was I, but for auto transformer it becomes 3I by 2. So the input voltage is same. So the new input power is 3 by 2 times the older input power. So what will be the new efficiency? It is P output by P input primed. Similarly, we can write like what the algebra we did here, 1 minus PL by P input primed. Now PL, as I said, the loss is same, is constant. So you can say 1 minus, now I substitute, Pi primed is 3 by 2 Pi. So PL by 3 by 2 pi. Now PL by pi is known from here. So 1 minus 2/3 of 0.08. If you do this, you will get 94.67%, which is close to this. So the funda in this question is the loss does not change and the input is now 50% more. So for the same loss, input has increased. So definitely the output also increased, energy conservation. So output by input increases because the loss is same and the efficiency increases. Is it clear?
Yes, sir.
Okay, we will go to next question. Okay, now induction motor. So that's all for transformers. Is induction motor. First question is 6-pole 3-phase 50 Hz induction motor is operating as 950 rpm. Okay, the speed at which the magnetic field of the rotor rotates with respect to, forget this, with respect to the rotor. This is not a scientific way to talk about these things. Just say with respect to the rotor, or sometimes we call it rotor reference frame. Okay, now tell me, if I have 3 coils in space. When I say in space, means these are 3 physical inductors which are actually kept like this. -120 degree shifted in space, and if I supply them with a balanced 3-phase source, what kind of magnetic field do they generate? So I have 3 coils which are actually placed like this. So this one will generate one magnetic field. This is generating another. This is generating another, and they are supplied by 3-phase supply VA, VB, VC. So the resultant magnetic field that we get here, how does it look like? Have you studied induction motor, Deepak?
No, sir. Previously, machine second in semester 4 I read, but we not seen any lecture related to induction motor.
Have you watched the lectures of this course related to induction motors?
Yes, access has, but not watch.
Yeah, sorry, what?
Lecture has in YouTube, but I not watch.
Okay, Rishi, have you studied induction motor? I can't hear you, Rishi. Did you say something? I still can't hear you. All right. I don't know if you have not studied this, then what's the point of, or not watch the lectures, and what's the point of solving this? So, what happens in this case is a rotating magnetic field is developed. So, if it is possible that with naked eye or something, you can see magnetic field, you will get to see that the magnetic field inside is rotating. You do not need any control, you do not need any converter, you need nothing. All you need is three coils arranged spatially in 120-degree fashion. You supply them with three-phase AC source, you will get a rotating magnetic field, and the magnetic field rotates at a speed of 120 f by p. That means, and this is in rpm, okay, this is in rpm. So in this case it's 120 into 50 by 6, 1000 rpm. So now this is called synchronous speed. But an induction machine is an asynchronous machine. It never runs at synchronous speed. So the rotor is rotating at 950 rpm, a bit less than the synchronous speed. Now what happens is, if the magnetic field is rotating in this direction in motoring mode, the rotor also rotates in the same direction but at lesser speed. It tries to catch up with the stator field but cannot, because if it can catch up, it will again slow down. Faraday's law. So this is 1000 rpm and the rotor is rotating at 950 rpm. So from the rotor, if you see, so you are now standing on the rotor. From the rotor, if you see, so this is what we see from the ground. The machine is mounted somewhere. From there you see. From the rotor, if you see that the field is rotating at 50 rpm. So this is the answer. In grid connected operation of a three-phase machine, the speed of the machine is observed to be 610 rpm. So what is the synchronous speed? Synchronous speed is 120 50 by 10 600 rpm. But the rotor is operating at 610 rpm. So how is that possible that the rotor is operating at higher speed than the synchronous? So definitely it is not motoring mode. Definitely it is not motoring mode. So it cannot consume active power. So definitely this cannot be a case. This cannot be a case. What is happening in this case? Basically what is happening is it is braking. Braking means negative torque. Negative torque means is the same direction but negative torque. So negative power. So it is giving power back to the grid. So delivers active power to the grid but consumes lagging reactive power. Induction machine cannot give leading power to the grid like synchronous machine. So this is the correct answer. Last question. Three-phase 60 Hz induction machine operates at some speed. Number of pole they did not say. We have to find out the number of pole. So we will assume this to be the synchronous speed first. Okay. Obviously, we will not get the proper number of poles. So 120 F by P is 684. So if you do this, what you get is something around 10.5, right? So definitely the number of pole, see, number of pole cannot be odd. It's either 10 or 12. But since 10 is closer, I will take 10 first and see once again. 720 RPM. So it's matching. How do I know it's matching? Because synchronous speed is 720 RPM and machine is operating at 684 RPM, slower than the synchronous speed. So number of pole is 10. That is confirmed. Okay, why not 12? You can say, why not 12? So 12 will also give you the same thing. It's okay, because the rotor, it's motoring mode. They didn't mention though. They will take in motoring mode. So this cannot happen in motoring mode. Why not 8? You may argue, why not 8? It's 900 RPM. 8 can also be perfectly fine. 8 can also be perfectly fine. But if you find out the sleep here, sleep in this case, sleep which is given by synchronous speed minus rotor speed by synchronous speed, the sleep here comes out to be 5%. Whereas the sleep here comes out to be, if I take it as a 8-pole machine, 24%. It's very unusual that induction motors operating at this sleep. The machine will draw excessively large current and it will burn out. Induction machine will hardly operate at 5 to 6% sleep at full load, not more than that. Even 5% is quite large, I would say. Okay, so this is the one. It's a 10-pole induction machine, we could find out. Now the rotor EMF makes 3 cycles per second. So it is called the sleep frequency. Rotor frequency, sleep frequency is 3 Hz. Three Hz. Oh, actually, they gave you here this data to find out the number of pole directly. See, what they wanted you to do is SF they have given you, AF is known. So sleep you find out. Sleep is 3 by 60, which is 1 by 20. It is 5% that we just find out. Now, once you know the sleep is 5%, it is, you know that NS minus NR by NS is 0.05. In this equation, NR is known to you. So from here, you can directly solve for NS and find out that it is 720 RPM. They wanted you to do like this, but in several places, you will see this data will not be given. You'll be simply told that it is happening like this. 3-phase 60 Hz machine, this much speed it is rotating. You have to find out in this fashion that the number of pole is 10. Okay. The same machine, when connected to this supply, frequency of the current. All right. So 3-phase 50 Hz. So now the same 10-pole machine is connected to a 50 Hz supply. So what is the synchronous speed? It is 600 rpm. So what is the sleep? 540 rpm. So sleep is 1 by 10. And SF, sleep frequency or rotor frequency, is 50 by 10, 5 Hz. If you want to solve more problems, actually, in some second or third class, someone asked me about um, book to solve problems. I told many books, but I forgot to tell the best book, which is so you make sure that you solve this book. Uh, by Parker Smith. You can simply go to the shop and ask for Parker Smith's problems book. They will give. So make sure that you solve this book. This is, I would say, if you solve the problems from this book, your basics will be crystal clear. There are several problems from several approach, attacking your basic concepts from several approach. It will do. So it's very important that you solve this book. That day, someone asked, I told so many books, but I forgot. I don't know how I forgot because I was thinking about basic electrical books. This somehow did not come to my mind. This is the best book, I would say, to learn basic electrical engineering and solve the problems. Okay. All right,
Yes,
we'll
sir.
stop for today. As I told that next class is tomorrow, next and last class. Tomorrow, 6 to 8.
Sir, please upload lecture today because we revision it.
Yeah, sure. But before you revise this video, you read induction machine from somewhere or see the lectures.
Okay, sir.
Okay, I will stop recording. I'll stop the class. Thank you.
Thank you, sir.